Hi, this is Nathan Tintle. In this video, we're going to learn how to write a paragraph comparing two distributions of data on a quantitative variable as presented in dot plots. We're going to address aspects of shape, center, variability, and unusual observations. To do this, we'll talk about the old, faithful Geiser dataset from the Introduction to Statistical Investigations textbook. Researchers measured 222 separate eruptions of Old Faithful Geyser over a 2-year period. They recorded the time until the next eruption, and you can see from this dot plot there's two separate clusters of observations. And while the overall average time from one eruption until the next is about 71 minutes, there's a very large range of times, ranging from as low as 40 minutes all the way up to 95 minutes until the next eruption. The standard deviation is almost 13 minutes. So the question is, if we're trying to predict Old Faithful, can we do better? What park rangers and researchers noticed is that the length of the prior eruption seemed to do a pretty good job of telling you something about how long it was going to be until the next eruption. So what we've done here is we've separated that previous dot plot into two separate dot plots. We're looking in the top dot plot at the time until the next eruption where the prior eruption was quite long. That is, the eruption's more than 3.5 minutes, and then you ask yourself, how long is it going to be until that next eruption? On the bottom dot plot, when the prior eruption is short, it's less than 3.5 minutes, we ask ourselves, how long until the next eruption? And what we can see is that those two separate clusters seem to be fairly well explained by how long the previous eruption was. But we want to go a little further. We want to write a paragraph that really talks about these distributions. And when you talk about distributions, you talk about four components: shape, center, variability, and unusual observations. And so what we're going to do now over the next few slides, we'll look at those two distributions side by side, and we'll talk about their shape, center, variability, and unusual observations. And then we'll put it all together in a single paragraph. Let's talk about shape. Let's look at these two different distributions and sort of compare and contrast their shape. In both cases, we would say these are somewhat mound-shaped distributions with a single peak. Neither one is perfectly so, but for the most part, these look the part of mound-shaped distributions. Now, the centers of these two distributions, while the shape was similar, the centers are quite different. After a short eruption, the typical time until next eruption is between 50 and 60 minutes. You can see that just by looking at the distribution. While after a long eruption, the time until the next eruption is between 75 and 80 minutes. Again, you can see this just by looking at the dot plots. But another way to talk about center is to compute the mean, or the average, for each of these sets of data, and you could use a computer or a calculator to do this. We've done that and found that after a short eruption, the average time until the next eruption is 56.3 minutes, whereas after a long eruption, the average time is 78.7 minutes. After comparing the centers, now we can talk about variability. After a short eruption, inter-eruption times vary between about 40 and 65 in most cases, compared to between 65 and 95 after a long eruption. Another way to compare variability is to talk about the standard deviation. We can compute the standard deviation of each set of data. Now, the standard deviation is the average deviation of each data value from the middle. So you're sort of saying, how close are these values to the middle of the distribution? So on the top graph, after a long eruption, the standard deviation is 8.5 minutes. While after a short eruption, the standard deviation is 6.3 minutes. So after a short eruption, there is typically a little less variability, though we certainly see some unusual observations, and we'll talk about those in just a minute. At the very beginning of this presentation, we looked at the standard deviation when the two groups were combined, and it was much larger, 12.8. The last thing we're going to talk about are unusual observations. There were a few unusual observations. One time, down here, the low end, we see this one observation here. What this means is after a fairly long eruption, there was one time where it was pretty quick. before the next one, only about 1 hour. On the other side, when we look here at when the prior eruption was short, there are a handful of times where it's more than 1 hour until the next eruption. And so while the length of the prior eruption does a pretty good job of classifying how long it's going to be until the next eruption, it's not perfect. There's still variability within those groups, and in fact, a few unusual observations. So let's put this all together into a single paragraph. So if we ask you, write a paragraph comparing these two distributions, here's an example. When comparing the distribution of intereruption times after long eruptions to the distribution after short eruptions, we see that while the shapes of the distributions are both similar, they're both mound-shaped, and they have similar variability, the standard deviation is 8.5 and 6.3, comparing the two groups. The centers of the distributions are quite distinct. After a short eruption, a typical time until the next eruption is between 50 and 60 minutes. The average is 56.3. In contrast, after a long eruption, a typical time until the next eruption is between 75 and 85 minutes, an average of 78.7 minutes. And while the majority of intereruption times follow this strong pattern, there are a handful of exceptions. A couple of words of caution. When we talk about distributions, this is certainly more an art than a science. This takes practice. And really, the key thing is don't focus too much on every little nuance of the distribution. There's going to be a lot of sort of spikes and valleys, especially in smaller data sets. The key take-home messages are in the general patterns.